And so there's going to be just say a lot of stuff today. So the idea now is to in this talk explain to you why. So the last couple of talks I was talking about definition of infinity modular operads, and so that whole definition was cooked up in order to approach this problem. So I'll just start with some really awesome math, like background stuff. That when I first heard this story, I thought it was just very cool. So it's got molecules. Right. So anytime I have an algebraic stack over a field and I pick a geometric point and x, I have a Galois action here. Right. So I have an action. So x consists of k. Those are the k points of my algebraic stack. And I can use the short exact sequence to define an action of the Galois group of k, k bar, the closure of k over k on the fundamental group here. Okay. And here outer automorphisms will come up. So these are automorphisms, but not up to conjugation. We're going to replace outer automorphisms with homotopy automorphisms in short order. So basically, if you take the outer automorphisms of a group, if I take instead the homotopy automorphisms of the classifying space of that group, those are the same. That's what we're saying. Okay. So the object we were talking about before, the moduli stack MGN, so genus G curves with n marked points, is defined over Q. And so I can use this exact sequence, in fact, to say that for any choice of rational tangential base point, I get a splitting and I get an honest action of the absolute Galois of Q on the Ital homotopy, Ital fundamental group of MGN. So there was this really beautiful paper. It's actually like a surprisingly easy proof. And some probably once you saw it, maybe not when you wrote it. Bailey, and it's like quite readable, even if you don't really know what these things are, because you work with Riemann surfaces. But the action of the absolute Galois group of Q on sort of the Ital fundamental group of the four punctured sphere M04. Well, this was actually so pi1 of M04 is isomorphic to the completed free group on two letters. And this Galois action here, it always induces an automorphism of the following form. Right, so x goes to some x to the lambda, where lambda is the cyclotomic character of some element of the absolute Galois group. And then y is conjugated by some word f, which we can find from our element of the absolute Galois group. And then z, which is x, y inverse, x times y inverse, is this means conjugate to. It just saves a little bit of notation. So we always have, so we know that the absolute Galois group acts on the free group F in a completely determined way. And we happen to know that this action is spatial, meaning that it sort of lives inside. So what
actually in the second, what does completed free group mean?
So this is a profinite free group. So the way you can think about it is just infinite words in X and Y. Potentially infinite words in X and Y. So now this theorem inspired part of Grothendieck's idea, which was to think about how we could translate problems about the absolute Galois group, this arithmetic object, into topological or algebraic topological. So in particular, the fact that this action is faithful, right, that this embeds in here into our automorphism group means that all of Galois Q bar over Q is somehow visible here, right? So everything that that happens in the absolute Galois group is living in some automorphism of F2, the completely free group. But this is actually a really simple moduli space. This is M04 is equivalent to P1 minus 3 points. And this is a little bit too simple. These actions are just sort of, basically they look like, you know, elements of F2 just look like going around the wedge of two spheres. And then we have the thing at infinity. So there's not like a lot of information here about these automorphisms. So there's not enough information to really get enough information to tell me what is the absolute Galois group. I can't write down new elements of the absolute Galois group with Q based on this information. So the idea was, well, actually, let's put together all of the moduli spaces for all genus and all numbers of punctures. And then we could exploit the natural maps between these moduli spaces, like for getting points, which we talked about a bit yesterday. And then when we look at the automorphisms of the moduli spaces that have to be compatible with these maps, this should give some constraint on how the Galois group acts. And it gives us a nice geometric, in fact, quite combinatorial setting where we could look and try to understand absolute Galois group. So this idea is what led to basically conjecture that there exists something which he called the ideal Teichmüller tower, which contains all the fundamental group voids, because this was Grothendieck, so group voids, but we'll stay with groups for now, of the Étale fundamental groups, and all the structure maps. Oops, that's supposed to say induced. Induced by maps between the moduli spaces. Right, so what should such an object be is kind of the point where we're starting this conversation, right? So there's some ideal object, and its automorphisms should tell me what the absolute Galois group is. Seems like an ambitious goal for 9 in the morning. Okay? So what happened, there's a version of this that showed up in genus 0, kind of in a different context. So Drenfeld was studying braided monoidal categories that arise from quantum groups, representations of quantum groups. But he noticed that, well, I mean, lots of people notice this, but the relationship between the pure braid groups, so that's what PBN means, and the fundamental groups of the moduli space, genus 0 with n points, right? So there's a geometric and an algebraic relation. So M0n, this is just n ordered points on P1 modulo the action of PGL2, which if you look at the complex points, just look at configuration, they look like configurations of points on a sphere. And so configuration spaces of braid groups, this is algebraic topology, so I'm just trying to get that in mind. So the relationship is both like geometric and algebraic, which is just to say that, as we talked about before, that the Étale fundamental group of M0n, well, this is going to be equivalent to the profinite completion of the mapping class group, genus 0 surfaces with n boundaries, which is equivalent to the pure braid group on n minus 1 strands, modulo the full central twist, or the ribbon braid group, which will come later. So, so Drenfeld was studying these objects, the pure braid groups, which don't know.
Sorry, can you say what the central twist is?
So yeah, it's just the center, modulo the center, I guess is the way to say it. So the center of the braid group, so, right, so PB, let's say 3, or I'll have, this would be X1, 2, X, I think, and I'm going to do this in the wrong order. Is the full twist around? Is that
The easiest is to draw it, but it's not easy to draw.
No, it's not easy to draw. That's the whole point of the slides is I don't want to be drawing stuff.
And even, yeah, you have to do full twist, so it's difficult to.
Natalie's didn't do it for me. It's the twist.
If you dance it, it's gonna work.
Yes, do a little dance later. That's the Ford talk, is the performance. So right, and so Jennifer was looking at these pair braid groups, and he actually wanted to find some relations between them to reflect properties of braid modular categories. And in fact, the relations he found were things that come from, they're reflected forgetting points on the configuration spaces, or forgetting points between the moduli spaces. So I could go from, say, M0n to M0n, where n is less, by just forgetting a few points. Okay? And what does that look like on the braid group? That looks like deleting strands in the braid group. Okay? And in fact, this led to sort of a tower. And by tower now, I literally mean a projective system of groups. So these arrows are actually multiple arrows. Right? So those arrows are doing some heavy lifting. This is a projective system of groups. Of braid groups, right, starting from PB3, where you can go all the way down. It's not interesting. And going up. Right? So we can delete strands in lots of different ways. Good. So if I look at this object, this projective system of braid groups, well, and I take its automorphisms, what happens? So any automorphism of this tower of braid groups that I've constructed, pure braid groups, which preserves strand deletions, behaves well with respect to sort of the natural symmetric actions of permuting the labels on the strands, and interacting well with any braidings that happen in groups. Well, this will be encoded by a pair, an integer, lambda, and an element of the free braid group, of the free group. Free braid group would be a new thing I'm defining today. Free group F2 hat, where this is what's called the derived subgroup of the free group. And what is this thing? Well, this thing is precisely the subgroup of elements, words, so infinite, possibly infinite words in X and Y, which define automorphisms of F2, and this formula was put up here for a reason, so it looks the same. Well, so any word here would define an automorphism where I take X to the lambda, Y to conjugation by F, and Z, which is XY inverse to something conjugate to Z to the lambda. So it's exactly Bailey's action. So any automorphism of this tower is going to be a pair that we would have seen in Bailey's action on M04.
Does the F prime depend on lambda?
No, I have the lambda here, so I could have said X. The derived subgroup just means I act by conjugating. That. There you go. I mean, it means lots of things, but that's what I mean for it today. So that the combined pair is giving me some action. And this pair, so any automorphism of this braid group is going to be defined by lambda and an F. And this lambda and F, we're going to have to satisfy something called the pentagon relation, which I've just written down so that it's there. An invertibility relation, which is that fxy times fyx is 1. And a hexagon relation. And there'll be a picture of the hexagon later. I should have said at the beginning, all the pictures that you will see later were drawn by Lucy, which is why they are readable on them. So, in fact, they're like really almost too pretty. So, all right. So the observation here was that, well, we used these this to define what's called the profinite version of the Grothendieck-Teichmüller group. So the profinite Grothendieck-Teichmüller group is the group of all pairs lambda F, right? So an integer, an invertible integer, and an element of this derived subgroup of F2, which satisfy the invertibility pentagon and hexagon relation. So basically what Jennifer was saying is I want GT to be the automorphisms of this tower of braid groups. And this is the object that sort of acts in a universal way on braided collineal structures. That's what he was trying to construct, but he just mentioned in like section 4 of this beautiful paper I cited here that this is related to what Grothendieck said should do. And then other people picked this up. So in fact, then Drenfeld conjectured and then Ihara proved, like, I mean, it's interesting, the papers are dated the same year, but given that the paper version of Drenfeld I have is the English version, I don't know how they, maybe they came out at the same time, but Ihara proved basically what Drenfeld said, is that there's an injective map of the absolute Galois group into this group GT, where the way you see that this map exists is you look at how the Galois group acts on the tower of moduli spaces from forgetting points, the fundamental groups of the moduli spaces, Bailey's action, and you look at how GT acts on this tower of braid groups, and that sort of induces an induction. So you have like automorphisms, and that, induction, induces and includes subgroups. So this profinite Grothendieck-Teichmüller group, we know it acts on this tower of braid groups that we can get a really good handle on. And we know that it acts exactly how we expect the Galois group to act on the modular space, on the genus 0. And in fact, what shortly after, again, in the 90s, there was a lot of really cool stuff coming out. Shot showed that the profinite version of GT is actually isomorphic. So this definition is actually isomorphic to all the outer automorphisms of the tower that Drenfeld proposed. Right, so they sort of wrote down this big projective system and they just computed. Then kind of in a totally different context, so George Barneton in the 90s, in 98 was thinking about, so there's a rational version of GT which acts on Drenfeld associates, which we'll probably talk about a bit tomorrow. I'm going to take requests for which variations of GT you want to hear about tomorrow, tomorrow, Friday, on my last talk. So there's a rational version that acts, this was acting on sort of universal finite type invariance of knots. And then a bit later, Benoit Fraisse, and then there's also a graded version of Wilwacker, where I forgot the citation. And there were a few others showed that this sort of pro-unipotent or rational version of the Grothendieck-Teichmüller group is actually isomorphic to the homotopy automorphisms of a rational completion of this parenthesized braid like that. Right, so now I'm replacing the braid, the pure braid groups with this sort of parenthesized model, so more like a fundamental group away of the little disk Operads. So this was used as a model for the rational homotopy type, automorphisms of the rational homotopy type of the little disk Operad too. So there's this, in other words, this, what I'm trying to say is this big projective system of braid groups. What are all those maps? Well, those maps are precisely encoded by the operad, by E2, right? So operatic structure, the operatic composition, and the unit, we're capturing what all these maps were supposed to be, right? Sort of, it's kind of like going backwards if you think about it, but it's, right? So the braid group maps are forgetting strands, and when you compose in a little disk, you're like adding strands, but it's the same, it's essentially the same structure. So this led to the idea that there should be this operatic way to encode the Teichmüller tower. Okay, so then Geoffroy Forel noticed that you could actually do the profinite completion of the operatic group voids. So that construction I showed you, I think yesterday, that's right. That was yesterday, and use this to show that the profinite GT is actually equivalent to, right now, homotopy automorphisms of just sort of formally rationally complete, profinitely completing the operatic parenthesized braids. And then via just taking classifying spaces and doing some homotopy theory, this is formally equivalent to the homotopy automorphisms of the profinite completion to whatever that means. Right? It's just a formal construction you do on classifying spaces. So inspired by this idea, Pedro Boveda and Geoffroy tried to actually take this back to the next step. Like, does this map to the Teichmüller tower? How is constructed? So this part, right, this profinite completion, once you take classifying spaces, becomes a bit of a nightmare. So we use infinity operads to model a genus 0 version of this Teichmüller tower. And this just used actually ribbon braids as a stand-in for the mapping class groups. So because the pure ribbon braid group on n-1 strands is isomorphic to the genus 0 mapping class with n boundaries. The indexing is driving me crazy. It should be either n+1 or n-1. I've been correcting that in this paper that I've been writing for about a year. And then every time I change it halfway, I get distracted and then I can't remember which one's right. That's the whole thing. Like a waking nightmare. But anyway, and this is right, sort of formally homotopy equivalent to homotopy automorphisms of the profinite completion. So this infinity operad, which is equivalent to the profinite completion of the framed U2 operad. So you could think about this operatic composition as capturing this Teichmüller tower. And then the idea is, well, what about higher genus?
Sorry, can I ask a philosophical question?
Yeah, this is all philosophy so far.
Yeah.
So
if I don't profinitely complete, then if I recall correctly, automorphisms of E2 are O2, like I can rotate and reflect.
And they're pretty trivial, yeah. You don't complete.
Yeah, so they're not very exciting. But then I guess I don't know, but like I feel like the automorphisms of frame E2 look different because I probably don't have this rotation anymore. So is that I guess maybe the completed automorphisms look very different anyway, but it's kind of curious to me that at least I think that without completion the automorphisms change when I go to the frame thing, but here they somehow don't. So
well, I mean,
the reason why they don't change.
Yeah, I mean it's kind of interesting. The fundamental reason why they don't change is just well, it's basically group theory. It's that, you know, if I look at maps out of PAB into any operatic groupoids, so this operad is generated, and that's actually sort of where we're going to go to the interface. This is the question, by two basic operations. So by braiding, so I'm going to try to draw a braid. That worked. And then changing parenthesization on the objects. And basically every morphism in the operad is generated by operatic or categorical compositions of this one, which is called alpha, beta, their inverses, and permutations. Right. So it's because I know that, and I have some finite presentation of the operad, so I know how to make any map. Right. I send the generators to something, and then I check that those generators satisfy whether the pentagon and hexagon relations. And then the parenthesized ribbon braid operad. Well, this just adds a single generator, and I'm not going to be able to draw it, so it's just like a full twist. It replaces my strings with ribbons, right? Because I have a framing, right? And so I have this one place to send how. And it turns out that once you forced all of the relations on PAB, it just trivializes how. So it becomes a group theory problem. And I don't know what the sort of topological reason for that is. It's just the automorphisms are, I mean, they eat a lot of structure, as you'll see either later if I get there, or if in Shannon's stock, it also kills the cyclic structure, like which you would think.
The tau and the braid are very closely related.
Yeah, exactly. They're very closely related because like if you compose, okay, it's if you think tau is the day place, which will happen later, it causes the full braid. They kind of the relations between them end up canceling them out in automorph. So I guess that's not really philosophy, it's group, but it just sort of happens. But yeah, same difference, right? I'm equally bad at both. So all right. So the idea was, okay, how do we think about all the higher genus things? Okay. And I will admit that at some point I actually thought this idea would be much easier than it actually is. So it became a thing. But anyway, so there was a paper in 2000, so inspired by the so thinking about, I know what braid groups are, and I know what E2 is. Ideas we're going to look for more of like a topological or groupoid approach to building a typing like that. So there was a paper in 2000 by Hatcher, Lashak, and Schneps, who were also inspired by this idea. So thinking about the connection between the mapping class groups and the tau fundamental groups, they wanted to take a topological approach to building this typing like that. So what was the idea? And we'll see a version of this later. So we're going to replace this tower of braid groups by some tower of topological groupoids. So built from rigid structures on surfaces. So they were looking at the a groupoid model of the Hatcher-Thurston-Pence decomposition Pence complex. So it's a two-dimensional CW complex built on Pence decompositions of surfaces, or objects of Pence decompositions of surfaces. So, but there are a lot of variations of these types of topological groupoids in the literature. So where you maybe take ideal triangulations or markings or things like that. So in the Hatcher Lashak-Schneps work, they build a groupoid whose objects are all isotopic classes, Pence decompositions of a fixed surface of type Gn. And their morphisms are finite sequences of elementary moves, and I'll show you some pictures of that as we go. And so this was based on a Hatcher-Thurston complex, but this thing is huge. I was going to put a picture and I couldn't find a good one, but it has like an infinite. Oh no, sorry, not this one. The next one. This one has 2G minus 2 plus n vertices. So a reasonable thing. If you want to include other things like relabelings, then you end up with complexes like this, but they have an infinite number of vertices, which is why I look so tired. All right. So basically, if you can organize these groupoids and include their natural gluing and forgetting maps between them, then you would have some type of topological model for some part of the typing. That's this philosophy, and it's actually quite a nice introduction to this paper that they write kind of why they're doing this philosophy. So if you want to see what this is. And of course, then how would I check if I had a good model for the Teichmüller tower? I need to know how the Galois group acts. And that's really hard. So what they do is check how GT acts on it, right? So if you want to propose some giant tower of groupoids and say this should be the Teichmüller tower, well, you need to know how the Galois group acts. That's hard, but GT is something we have a presentation for, so let's try that. So that's basically the philosophy going on here. Right. So there were a bunch of papers after this in the early 2000s, sort of studying variations on this Hatcher Lashak-Schneps tower. In particular, the one that we'll focus on today, it was introduced by Nakamura and Schneps. So what they did was they introduced these groupoids, which had an infinite number of objects based on a complex of like what they called scene surfaces. So tons, they had all the Dane twists, all the relabelings, all this information. So they built this huge, it's still a simply connected complex. It's huge, and you can make it a groupoid, why not? And then they found out that if they looked at how GT acted on it, they actually got an additional relation, which encoded sort of how the Galois actions act on licorice twists. So these weird little symbols here are coming from what happens in genus 1. I won't get into it. But they defined a subgroup of GT called, I'm just calling it NS. They called it G, so G for group. I'm not the only one who just gives random letters to, but anyway, so I'm going to call it NS for Nakamura-Schneps. And this is a subgroup of GT. We don't know if it's a proper subgroup, but it's a subgroup, and it contains absolute Galois. So they proved this part, which is why these are Kummer-1 cycles show up in here, right, in order to contain the absolute Galois group. So this is the subgroup of GT given by pairs F and lambda. So they have to satisfy the pentagon, hexagon, and stuff, and then they satisfy these two new relations. tell me something about what happens in the once punctured torus. Okay. So now actually, there's some ideas. So we wanted to look at what they did and try to make it into a modular opera. That's where higher genus surfaces show up. And so the idea is to build a modular opera out of topological groupoids that's kind of inspired by these groupoids. But we also want to like compute their automorphisms, so we need them to have nice homotopical properties, right? In particular, I need them to have a finite set of objects. We build a groupoid that models surfaces of genus G with n+1 boundaries. But I need a finite set of objects, as we saw with our profinite completion procedure. Okay? So I can't have this infinite number of vertices in my complexes. And I really want it to be nice homotopically. So I wanted it to assemble, I want a cofibrant modular operating groupoids. So when I compute homotopy automorphisms, it's not so bad. And you know, I also want it to be geometrically meaningful, so we wanted to have the following chain of equivalences in the infinity category of prospaces. So, right, that if I take the profinite completion of this groupoid after taking the classifying space, it should align with this, the profinite completion of the classifying space of the mapping class group, which is the classifying space of the mapping class group. And I won't lie, this is actually the hard one. So, this one becomes obvious once you see the description. Actually, timing actually worked where I thought we would be. Okay, so let me tell you how we built these groupoids and this modular opera, and try not to scare you away from topology. Right. So, what do we have? Let's just get some language on the board. So I'm going to say that a surface of type G of genus G1, sorry. A surface of type G n+1 is going to be a compact oriented surface S with genus G and n+1 boundary components. I want every boundary component to have a little collar, a nice little neat embedding. This is so when I glue them together that I have a smooth surface at the end. I'm going to enforce a labeling. So I want to have a surface with a labeling of the boundary components, starting with 0. I can't remember why we made that choice. But anyway, starting with 0 and going to n. Oh, because we compare with Operads. And so I'm going to keep every boundary has a label and it stays with that label, it doesn't change. And then I want them to be parameterized. So on each boundary, I'm going to fix a particular mark point so that I always know where I am. Okay, so my surface comes with decorations, just like my graphs on purpose. All right, so here's my example of my standard pair of pants. All right, so surface of type 03. I'm going to have, we're going to be embedding some trees in here, where the boundary labels go with the labels of the edges, and the marked points, so the tree embeds on my parameterization mark point. So what I mean is my parameter is here, and so I can keep track of it by embedding a tree into the surface. But I don't do. That's actually a little bit of extra data, but we'll keep the picture. And in fact, so embedding these trees or these simply connected graphs into genus 0 surfaces we're going to make this useful in a precise way. So if you really want to describe, so we're going to want to build a groupoid, and the groupoid's objects are going to be these surfaces with a labeling and some parameterization, and then I want to look at diffeomorphisms between them. Right? And so there are different surfaces. You can actually figure out what that is, but it's very annoying. And I would say that Lucy went through various ways of telling you how annoying this was before we arrived on this model. So there's a way that we can do this with a diagrammatic model. So I'm going to give you a precise thing. We're going to use embeddings of trees in here to be able to say specifically based on what happens to this tree, what this diffeomorphism is. So I'll put this up here. Well, if I have two surfaces, S and S prime, they've got labelings and they have their parameterization points. And I'm going to embed a tree, T into S and T prime into S prime. So this is a simply connected graph. I'm staying in genus 0 for now. So here, if T and T prime have the same cyclic ordering on the boundary components, then there's a canonical up to isotopy boundary fixing diffeomorphism from S to S prime, which we can construct as follows. Right? So you cut a tubular neighborhood around the tree, about each of them. And then we have a bunch of disks. Then the cyclic ordering determines a boundary diffeomorphism on those disks. And then basically glue things back together. And this gives me a way to get a diffeomorphism here. And this is unique. Right, I put the lemma here. Yes.
I mean, it is because the complement is a disk.
Because it's two div and genus 0 and everything's there. So yes. Not world changing, but extremely useful. So, oh, here's my Lego. That's not the Lego. Okay.
But
So
that doesn't work in IHG.
It does not work. Genus, no. So that's only for we're going to be sort of cutting things down to genus 0 doing the computation. You have to handle genus 1 a little bit different. So again, so what we're going to be doing is using what I just showed you, and then something called a cut system. So so the standard idea, or the Lego part of this talk, is to build a two-dimensional CW complex encoding how you can cut a surface into pieces. So roughly, and I'll give you a precise definition of what we want, a cut system is a finite set of simple loops on the surface, the isotopy, so that if you cut along those loops and take the closure, you get a disjoint union of subsurfaces, right? And that's the Lego part. Type. Is this looking at what happens when you cut these things apart? So, what do I'm going to have a particular type of system, which I'm going to call a marked cut system. And that's because this is what it's called in a source paper that's as close to what we wanted as we could get. Okay. So, start with my parameterized labeled surface. I'm going to have pairs. So C is a cut system. So my finite collection of simple loops. And I want this to be genus 0 surfaces. So I'm going to cut my surface into genus 0 parts. And then I'm going to actually give an embedding of a simply connected graph, such that the combinatorics of the graph match the cut system. Right? So I want the inner edges of G to map to the curves in my cut system. I want the vertices to map to the connected components of the resulting thing, and I want the I should say neighborhood. The size of the neighborhood of my vertex, the number of edges adjacent to each vertex to correspond with the boundary components of the resulting. Okay. There's a picture coming up. And that the leg maps will be sort of corresponding to mark points on the boundary. And for each component, and this is kind of important, right, this marking will restrict to an embedding of the appropriate corolla of the vertex. And I want that vertex to carry a marked edge that gives me a cyclic ordering of the vertices. So we're going to denote that with a, that's why I was saying I had in my graphs, I wanted to have an ordering around the vertex and an ordering around the boundary. They don't necessarily have to be the same. Okay, so our definition, and I'm going to show you a bunch of pictures now, so this looks a little bit weird, is we're going to have a cut system. We're going to build a complex where we have we've taken a cut system so that our surface S is always decomposed in 3 pans. So we take the maximal one. Right? So we're going to build what we call the complex of markings over pans decompositions on pans. So this is going to be a 2-dimensional CW complex. The vertices are the set of all marked Pants decompositions on S. So all trees that decompose, trivalent trees who decompose S. And the one cells are given by a bunch of edges that I'm going to show you. So some of them will be the obvious ones. And like Dane twists, which are called T moves in the paper we were using. So here, this arrow is emphasizing the fact that here's the vertex on my graph I've embedded, and the arrow points, I want the cyclic ordering of vertices. This is my distinguish. So it's not a rooted tree, it's the sort of ordering I have on the vertex. So think of the arrow is always pointing toward whatever is 0 on the vertex, but not necessarily 0 on the boundary. Those can be different labels. So in this case, though, luckily nothing weird happens. Let's see so in a few minutes. So what happens is that, right, so I take my Dane twist, and this changes the embedding of the tree, but preserves the cyclic ordering. Yep.
Is it the 1 or 1, 2? Also right.
I'm sorry?
Also right picture, is it the 1 or 1, 2?
Oh, it is actually supposed to be 1, 2. Because that's not a braiding. That's the next one. So thank you.
Sorry, can you say what the cyclic order is?
Okay, so remember my trees, my graphs, they have a vertex and they have a neighborhood, and then they also have labels on the edges. So here I'm saying that this is, oops, I have this. So here, I'm saying that the neighborhood is 0, 1, 2. It just so happens that the boundary is also labeled 0, 1, 2. I'll show you one in a second where it's not exactly the same. So what I mean by the ordering is here, and I'm always going to want the ordering on the boundary to be 0, 1, 2. It's just I'll put the arrow in the direction of which one is 0, but on the vertex.
Underlying cyclic ordering due to the surface.
It's because of the embedding in the surface.
But then you're picking an extra.
I'm picking an extra
I
parameter.
really like to have numbered things.
I just want to have
I've said this every time.
There's way too much data because, well, so this thing, if you don't have all this data, then you have to have an infinite number of objects in your groupoids. So you can pick your harm, labels or infinite objects, and I pick labels. But you can do you. That's makes you happy. All right. So the braidings or B moves, as they're called again in the surface. So this is what you would think. Now the labels on the boundary are correct, right? So again, I have, I'm just saying, well, this is what happens if I do a half twist around one of the boundaries, right? Those are braidings. So I'm also in, if you're familiar with this Hatcher-Thurston complex, like the braidings aren't in there. They don't have A moves, S moves. So keeping these. You can think about it as just changing the labels on the boundaries, but it actually, we want to keep track of the full twist or the half twist. Right? And then A moves. So actually this would be better if I just show you the picture and then I'll come back to the definition. So these are where I have a surface of type 04. So 2 pairs of pants, right? So here, this curve here, this is the curve of the cut system. So this is the same surface with the same labeling, but a different cut system and a different embedding of a graph. And here I am choosing to have different orderings on the pair's pants, because this is actually sort of what happens to when I do this diffeomorphism, this is what happens to the ordering on this. So if I keep track of this information, then I can use that diagrammatic thing that I showed you before to specifically choose this A, right? Because A moves are not unique. I'm drawing a unique one, and often you'll see this in a paper and you think there's one, but you know, there can be Dane twists around each around this cut system when you do this diffeomorphism, and I want to be able to capture all of them. So
Is this supposed to be a cyclic? What is it?
So
You inspect the label of the boundaries?
the labels of the boundaries are fixed. So I want the diffeomorphisms on the surface to always just keep the labels of the boundaries, and just the A-move supposed to take this cut system. Sorry, here's the actual definition.
Tree doesn't go to the tree.
The tree does not go to the tree. That's the sort of right. The tree, even if we were thinking about this in terms of like gluing pens, we've changed the way we glued a pair of pens together. But in fact, it changes more structure in the tree than that. Like it changes the local labelings and things. And again, sometimes it's exactly what you want it to be. There is a standard A move, like the basic one, where this where you have this guy and this guy goes to this guy and that guy. That's great. Like there's a standard one, but they're not all that way. And because they're not unique, and you'll have Dane twists around this curve and things like this. So we're keeping track of all that. Quilt adjustment is what some people would call it. So there's like an A move plus something, which is usually some half Dane twists around this first curve. I mean, you can uniquely determine how many half Dane twists around that happen. Right. And then an S move. So this is happening on the torus. And this is where things get kind of annoying. So I'll just show you the picture again. So here, this is a map that changes this sort of embedding of a graph here. So I'm thinking about this being a tree where I've just glued two edges together. So here's this cut system. This makes it a pair of pants, but I could also cut here. And so if I want to, this changes the embedding. Now it's sort of a curve around here. And I'm keeping track of the ordering. Yeah. So what this looks like, this picture, is this is the mapping class acts on the homology of the torus by this matrix. So, right, so this is the standard S move. And this is the one that's a little bit hard. You want to capture this as some kind of modular operad operation, okay? But, you know, gluing together two edges of a graph is gluing together two edges of a graph, but these are clearly different. So we want to keep track of that information. Okay, and then the last one is, of course, we can always do cyclic relabeling and we can change the routing. So you can have these sort of internal twists as well happening on the surface. So you can think of this just, you can relabel the boundaries by a cyclic action, but you can also relabel the vertex by cyclic action. And all of those are the edges of this complex, right? So the vertices are just the Pan's decomposition of the surface. The edges are all of these things. So we have now an infinite number of edges, but a finite number of vertices. So
Why do you have a finite number of vertices?
So because we fixed a surface and then we took sort of all the different cut systems. Oh no, actually we still have an infinite number yet. So far, still, yes. We still have an infinite number. We have to take some slices. Yes. So if you take the graphs without the labeling changes, then you would have, so if you just look at Pan's decompositions of a space, there's a finite number of those. So given a surface of genus G with n points, there's like 2G, no, it's like 3G plus n. There's some
Up to isomorphism.
Up to isomorphisms. There's some finite number. Okay, so the cells of the marking complex, there's 9 possible loops that give 2 cells. And one of them, of course, looks like the hexagon. So tried really hard to make fit on this side. And this was actually a pretty one. So I said Lucy made all of these, so they're very pretty. So which are all the ways in which you can do B moves and A moves, and then you end up in a loop. And there's 9 of them, so it's a bit more complicated than 4, and we'll see another one in a sec. Yeah. All right, so I'm going to use this to build a groupoid. And I'll just use one more thing, and I'll finally tell you the definition of this thing. timing is almost in the right place. So if I give you one of those labeled decorated graphs G that I had presented in my modular Operad definition, I can build a label parameterized surface from them. So you take SG, this is my surface based on my graph, and the marking is given by basically a Pants decomposition that I give you by embedding the graph into the surface. So basically I take a graph and then I just do this. Okay. But I have extra information about how the graph is embedded there, including all because I have all that labeling. So it could be a more interesting version. So each graph kind of uniquely determines the surface with the marking. And I can glue these, this has a Pants decomposition where the pants were glued along the internal edges of the graph. I have the labeling of the boundary, and I have the embedding, which gives me sort of how the graph is living, the cyclic order. It's maybe too much information or not enough, but let's say. Okay, so here's my object. So I'm going to say define a family of groupoids. So S01, which is basically the cylinder, is just going to have a single object, which is my edge. And the morphisms are isomorphic to Z. So this is a copy of the Dane twist around what's like the thin cylinder. It's took from a paper of Nathan's. And then if I have higher for all other arrangements of G and N, I'm going to have objects of my groupoid. Well, I'm actually going to take the free modular operad generated by this guy. This where the genus 0 vertex. So I'm going to have genus 0 vertices throughout. And I'm just going to have a bunch of basically trivalent graphs, but because it's a modular operad, I can also have things like this. And so each G comes together with a labeled parameterized surface, according to whatever my labels were on my graph. And yeah, I'll take my morphisms and my groupoids are then the diffeomorphisms between those two surfaces, right? And I'm computing those at the genus 0. So this thing, these groupoids, so I have a nice finite number of objects. If I look at how many graphs can be generated by this genus 0 corolla, and I look at all the labelings, that's a finite number. Very nice. And then I have the diffeomorphism between them. So here I can act by the symmetric group just by permuting the boundary components of my graphs. That induces cyclic, sometimes cyclic or other permutations of the boundary components. Yep.
Can I check the so it's a modular operad with one color?
One color.
And now in arity 3, it's going to have like 6 objects or something like that, because I can take the corolla and like the corolla that is the generator is like different from its relabelings, right?
Yeah, so okay, there's actually and I debated putting this slide in here. So we actually we're very strict about how in arity 3 or genus 0 arity 3, we actually only want to have precisely 2. And so we take like a quotient. So we take the free modular operad generated by 2 things, where the cyclic group acts trivially on them. So you take like a quotient of the what is it called? The symmetric group. So I want precisely these 2. And no more, and these will generate everything. And I gave them special names, and they generate. So it's actually the free modular operad on 2 things, sort of to eliminate. It's actually weird if you allow it to be just all of the labels. It it messes up the cyclic case. I don't know. We get something that's not isomorphic to the cyclic frame disks. It's much, much larger. But so anyway, I specifically didn't put that, so I didn't have to regret it. So you have to be a bit careful. So it's basically trigonal graphs with a little bit of extra information as the objects. And then I have diffeomorphisms between the surfaces.
It's planar. It's because
Yeah, so they are planar because I labeled all the vertices and there's labelings around. I mean, there I can give you like a.
but I mean these are different.
These two are different. Yeah, these two are different as planar trees. No, I'm glad you think so.
It in the surface, right?
Yeah, we're going to throw it in the surface, so they're not real things. They're just combinatorics. But yes, these two are different, and but then sort of however you act on them by the symmetric group, like so you can have a map that goes from here to here, but the cyclic thing will act trivially. So we're like forcing this to be true, and then we take the free modular operad on that set of operations. So you might expect something different, but we take the quotient set. It's still free, which is really good for us homotopicals. Okay, so we basically build operatic composition now by gluing together the surfaces. And this induces maps on the mapping class groups. And I'm running out of time, so I will just say what happens. So, and now this thing has a nice relationship with the marking complex, which is that if I take a slice over a particular graph, okay, I get a groupoid. I get an equivalence of categories. If I sort of took a two-dimensional CW complex, thought about it as a groupoid, I can build an equivalence of categories. Why is that useful? Because now I have those 9 loops that sort of generate the 2 cells of this marking complex. And that tells me how I have generators and relations of my groupoid. So I can actually like give a finite presentation for the whole modular opera. Okay. So I'll just summarize it quickly, which is that so using the equivalence, this sort of equivalence of groupoids, then the standard edges, the T moves, the B moves, A moves, and S moves, give us 4 like generated morphisms of the groupoids, which are the twist, the braid, and alpha. So those are exactly the ones I wrote for the PARB. And then sigma, which is some new morphism for the S move. And then, in fact, every morphism in this modular operaad is obtained by sort of operatic composition, contraction, and permutations of these morphisms. So in fact, the whole modular operaad is generated in genus 0, and then with 1 additional morphism. And so this, if you truncate at genus 0, we get exactly the parenthesized ribbon braid operaad with this cyclic structure that either Champion or I will tell you about on Friday. We'll discuss divide and conquer. And then, or to say that it's a cofibrant groupoid model for this cyclic frame little disc operaad. So this is equivalence to kind of what would happen. It's not exactly the same as the ones you'll find in Bunny or this other paper, but it's equivalent to. So it has a relationship back to that. And like I said, you use this complex to force relations. So here's one of the genus 1 relations, which is that, you know, we have some loop like this, where these are the graphs that are embedded. And I didn't draw the arrows on there, which helps a lot in here calculating. You get these types of things that we can actually check then what happens. So what am I thinking? I want to look at how GT might act. I want to look at how the I want to look at the automorphisms of this modular operaad. So I have a presentation. Yes. This is actually the last slide. So the question is, maybe the Teichmüller tower can be a modular infinity operaad. So you can check that this thing is automorphisms of this thing are determined by genus 0 and 1, that comes from the presentation. So you only have to compute what happens to automorphisms of the truncation, which is good. This higher genus stuff is not so good, for me anyway. And I guess no judgment on like the genus 2 surface. I just don't know how to deal with it. There's a natural action actually of this Nakamura-Schnepf group on the automorphisms of S. And this actually restricts to an isomorphism of GT with the genus 0. So it's sort of incorporating what we know about how the Galois group will act on the genus 1 part through this one group. And it restricts to exactly what we expect in the genus 0 part. And, you know, if you hit this with the classifying space functor and do some, I will say, deeply unpleasant arguments about getting the profinite conclusion to commute classifying space function, then in fact the sort of induced action, right, so the Galois group of Q lives inside NS. It acts on this now. This now is an infinity modular operad in pro spaces. This is non-trivial, and at least the things that we can check agrees with our sort of the expected Galois actions on M04, 05, 11, 12, which are the only ones I know. Right. And that's it for today. So there are a bunch of references, and there are many beautiful survey articles on the arithmetic part of this, if like you're actually interested in it. There's a really big thing in the 90s, and some people wrote beautiful papers. I mean, beautiful like surveys. You will get lost in it and realize that if you wanted to do something on your own, then it's way too hard, but it's still really pretty stuff to read. So I put a bunch of surveys in here, and if you want to procrastinate, you do that.
Other questions?
You expect this embedding to be an isomorphism?
Depends on the day. Maybe. So up to the fact of how you can define the group and S can change. So so there's a little bit of fuzziness on like how this how the genus 1 relation was defined. So if you sort of tweak the definition, then there's an isomorphism. Now, of course, is that the same group? It sounds like it should be really easy, and saying I have two presentations of a group. Can I check if they're isomorphic? Then you would be better at math than me, because it can be really hard. So this thing is isomorphic to something that is almost exactly NS, but has a weird extra twist in it. Is that also equivalent to GT? We also don't know, right? But all these relations that we have could degenerate in some sense.
Wait, which of the theorems was the question about?
The question, so I mean, the question is, so here we're giving a modular infinity operad. Oh, sorry, this one. Guillaume was asking about, should this be an isomorphism? So there's something isomorphic to this that is almost this, plus it has like a little twist. It has basically run off by like a Hackney twist, but it just will not stop. So maybe it's there, maybe it's not. So there is something that's isomorphic to this that's almost this. But again, even we don't really know. So NS is a subgroup of GT. We don't actually know that it's proper subgroup. It's possible that this thing that happens on the once punctured torus, this new relation could degenerate, right? Because the mapping plus group of the once punctured torus is isomorphic to the gray group on two strands. So these automorphism groups might be actually just like the same. But that's a very, very hard question to answer. But the idea of the Teichmüller tower was saying, well, okay, at least we have something that at least has the topological type of the objects we want. We have structure maps between them given by the infinity modular operad structure. And at least we know that it sort of looks right. So I think if you modify this in the correct way, you might hit something better. I will leave that as an open challenge. It's been an emotional ride on this problem, but